Welcome to Breadboarding. This is video 39 in the Breadboard 88 PC series, and in this video I'm going to be looking at adding the real-time clock and CMOS setup. So in our high-level plan, we're now moving on to the final phase where we're hopefully going to be able to get an early version of Windows to run eventually. But in this step, what we're going to be doing is adding the real-time clock and CMOS setup. The original IBM PC and PC XT didn't have a real-time clock, and so every time you booted PC-DOS or MS-DOS, you had to put in the correct date or time, otherwise all the date and time stamps when you write things to floppy disk would be incorrect. The PC-AT was the first IBM computer to introduce the 286 processor. It also included battery-backed CMOS memory, so this allowed the PC configuration to be stored in memory with a checksum rather than using dip switches to configure memory and all those sorts of things. Generally, we accept that PCs have a BIOS setup utility to maintain the CMOS settings. However, the PC-AT, when it was first released, just had a diagnostics floppy disk with a setup option. The XI8088 BIOS does have a simple setup screen built in. If we just have a look at one of the simulated PC-ATs on the PCJS website here. So this is simulating in JavaScript PC-AT. It's a great site to play around with if you want to look at old style computers without actually having to have one. And what we can do down here is if we load the IBM PC-AT diagnostics disk, PC-AT, and we'll load the PC-AT diagnostics. So when we load this, we need to reset this a couple of times before it actually boots up. The first time it says power off your system unit. I think that's so it goes through the full power on self test. Then we can see here, this is our diagnostics disk. Now in fact, what you needed to do to set the time and to change configuration, so if you added extra memory or changed the graphics card, for example, you would have to go into the setup. It would ask you if the date and time was correct, and you had to type it in the US date format, and then also the time as well. Then if you were happy with that, you could then save the date and time, and then it would actually show you the configuration. So this particular sort of virtual machine, if you like, has got twin floppy disk drives. I think that's a 47 megabyte type 5 disk, 64K of memory. And if you weren't happy with that, you could then go in and change this. So this is the way how you would set up your CMOS options and to change the time. So when we reconfigure the XI8088 BIOS that we're using for the Breadboard PC, we should actually see a similar sort of simple menu system for configuring the BIOS. So the PC-AT and the compact Despro 386 use this particular real-time clock chip. Now this had a 5,000 nanoseconds, so I guess a 5 microsecond cycle time. So there needed to be a bit of a pause between doing operations on this, and you'll see in some of the code that there may be quite a few no operations or jump to places further down in the code, which is normally used for doing delays in the BIOS. Now modern real-time clock chips are register compatible, and the one I'll be using is a Dallas Semiconductor DS12855. This has a 385 nanosecond cycle time, so it's quite a bit faster than this one, and this is the one which is used on Sergei Kislev's XI8088. So the CMOS and the clock battery are backed up by a 3-volt CR2032 button cell. The real-time clock uses IRQ8 active high. Now the real-time clock output is actually active low, and in fact it's also open collector, so we do need to remember to include a pull-up resistor on this, otherwise it won't work. Because we're using interrupt 8, this is one of the reasons why we need a second programmable interrupt controller on the design so that we can handle interrupts above 7. Now the IO port range is going to be 70 for the address and 71 for the data. So we set up the address we want to talk to, and then we read and write the data on the other port there. Now the original design did have a power supply good input. What that was used for is inverting that and then driving the chip select. So the idea of this is to prevent the CMOS getting corrupted under low power sort of situations. Doesn't really matter too much for our design here. I don't think we're expecting to have that sort of problem. So if we take a look at some of the designs, so this first one comes from the PC-AT design, and we can see here this is the power good input. It's inverted, then goes to the chip enable. Now we can just wire chip enable to ground, and I think that's what the Sergei Kislev design does. There is a bit of stuff up here, this is all to do with powering these two chips actually from a backup battery when the power is off. Now the modern chips don't require this sort of stuff, and also you can see here that in fact the 32 kilohertz oscillator which is used here to drive the time signal is actually done by an external chip here, which again we don't need to worry about. The key things we do need to note here is we've got the pull-up resistor for the open collector output on IRQ, and then it's inverted to actually feed the interrupt controller which uses positive interrupts. So if we go on to look at the compact Desk Pro, which use the same chip, so you can see here we got a slightly more complicated power circuit providing power to these bits here, and again this is using inverters to actually do the 32 kilohertz oscillator feeding into this. And then finally, this is the extract from Sergei Kislev's XI8088 design, and what we can see down here is the real-time clock with hardwired reset. We've got the Motorola Intel option here, so if this was pulled to 5 volts or high, this would implement sort of Motorola style clock signals. If it's not connected or connected to ground, then it will actually be the Intel style of bus signals. And you can see here that in fact there's an address strobe, there's a data strobe and a read write here, and these are actually driven by these 3 signals up here which are derived by the logic. So what this does here is just decodes, these 2 outputs are decoded to 7.0 and 7.1 in the IO address range, and then this combination of logic actually provides the address latch enable, the real-time clock write and the real-time clock read signals, which then feed into here. So we'll probably look at using a programmable logic device, a PLD, for doing this decoding, and what I will also do is try and make sure that decoding can also be used for the IDE hard disk controller, which we'll be looking at in the future video. And you can see down here we've got the button cell backup battery, so this is quite a bit simpler than the other circuits. So you see all this circuitry here handling the battery there and this circuit here. In this particular case, this is all contained within the modern chips, so all we need to do is to provide a button cell input to the VBAT there, and that will actually keep the clock going and the CMOS memory backed up when the power is off. So as I said, we need to worry about this inverter here and probably also a pull-up resistor just to be on the safe side. We can connect the crystal directly to the chip, so hopefully when we won't have any trouble with getting this oscillator to vibrate, and we can just plug it straight in here. So really it's a relatively straightforward addition to the project. We just need to hook this up to the data bus, do the address decoding with some sort of PLD up here, feed these signals in, and then the software for this is actually slightly more complicated, but because it's already built into the XI8088 BIOS, all we need to do is to reconfigure the BIOS to add the real-time clock, and hopefully then when we rebuild the BIOS it should then have all that support in. So if you just have a quick look at the datasheet. So this is the Dallas Semiconductor datasheet, and this is still available from Mauser and other, this is a current component, so you can buy it brand new. It's a drop-in replacement for the IBM 80 computer clock calendar. Now, it is actually quite complicated. The internal registers and things is really quite complex, and if we just scroll down to the pin descriptions, we'll see that you can see here this is the Motorola Intel bus timing. The pin has an internal pull-down resistor, so really you don't need to connect it to anything, but we'll probably connect it to ground just to be careful. The chip select, as I said, we're just going to tie to ground. We don't need to worry about that. So the address strobe, the read write, and the data strobe are what we're using for our control signals coming out from the IO read, IO write, and the address selection. Then the final thing here is we look at the interrupt. You see here the IRQ pin is open drain output or open collector and requires an external pull-up resistor. So we're going to put the pull-up resistor in there, and then it also tells us about the battery backup there, and also then the low RAM clear. So this is the clear CMOS. So on our design, if we actually short out the pin to ground when the power is off, then this will clear the CMOS RAM should we ever get any sort of corruption, or we want to show what happens on the boot up to see whether or not the checksum matches and whether or not it goes into the CMOS setup. Okay, so now I'm going to look at the KiCad circuit diagram, and then we'll look at laying out the board and looking at the chips that we're going to use. And we're going to need to make a small sort of button cell adapter to plug into the breadboard for the backup battery. So here's the main KiCad schematic for the breadboard PC as it stands at the moment. I had a few questions about whether I can upload this onto GitHub. Unfortunately, some of the earlier updates, I think of KiCad 8, seem to have offset a lot of the components, so they're not actually matching on the 0.1 inch grid, so it kind of messes things up somewhat. And when you're changing the bus connections, after every 1 or 2 bus connection changes, it seems to crash the schematic editor, so it's taken quite a while to sort out. So I'm waiting until the next KiCad update. Hopefully we shall sort that issue out. So if you're not familiar with this, then around this section of the board is our video controller. We've got the processor over here, RAM and ROM over here. Over here are the interrupt controllers, DMA and timers and various other things. Then we've got the keyboard controller, floppy disk controller up here, and the LED keypad display which is used by the monitor down here. So what we're going to be doing is adding a board down here, and we'll probably add the IDE controller down here as well at some point in time. So it's a fairly simple change. All we've really got here is we're taking the address bus and the data bus down here. So this is a programmable logic device which we're taking in the IO read, IO write, and there's a signal here which comes from the other decoder that just tells us when all of the A12 to A19 address lines are 0, so it makes it easiest for us to decode the IO addresses. And what this is actually doing is providing the control signals, so the address strobe, the RTC write, the RTC read, providing those signals over here, and it's also taking the interrupt. So this is the active low interrupt with the pull-up resistor, and it's inverting that, and this goes over to the other side of the board where interrupt 8 goes into the second programmable interrupt controller. We've also got A0 coming down here. Now when we add the IDE controller, we're going to need A0 to A3, so what I'm probably going to do is to put some sort of connector down here so that I can have all of those signals come in from the main board. And then we also need to feed in the data lines down to here, put in our little watch crystal here. So this is a very small crystal, does our 32 kilohertz. And then what I've also done is made a button cell holder to plug into the breadboard here. And for clearing the CMOS, we'll just have a bit of black wire. If we just plug the wire to ground when the power is off, then that would clear the CMOS should we need it. So hopefully this should be fairly straightforward. We will need to reconfigure the BIOS to add support for this. So if we just have a quick look at the components that we're going to be putting together. Okay, so we've got our Dallas semiconductor timer chip. It's quite difficult to see the writing on here, so I won't try and show it because it's faint enough to see it even when you're looking at it close up. So we've got chip labels. I've made chip labels for the RTC and also for the programmable logic device. So I call this, I think, IO decoder 2. So this is providing additional IO decoding signals. So those are 2 chips. We're going to need to program that in our programmer over there. I've got the watch crystals there, so they're very small, but hopefully those will go in one of the pins there. This is the button cell holder I've made. So it's very simple. They're just sort of positive on this side, negative on this side, and the strip board, only one of the pins on each side is actually connected. The other ones there are just providing stability. And the way how this works should allow me to plug it in so that we can plug it between the ground rail and the VBAT input. Button cell, and then I've made up some cables. So there's a 8-way cable for the addresses coming in here with sets of 2 to plug into the bus rails, and then this is the A0 to A3 address lines, and then we've also then got the data bus, so that will go into the RTC chip, and then we've got sets of 2. So I made up those cables as well. All we need to do now is to put on the chip labels and to program the PLD. I'll just show you the PLD configuration options first. So here's the PLD configuration for IO decoder 2 version 1. So this has been created for our real-time clock, and it will also be used for the IDE controller as well. So you can see down here we've basically got our I/O inputs, the address lines, and then the outputs. Then the logic rules down here, we're inverting IRQ8, and then we've got the address enable, write and read signals also in there as well. So we're going to compile that in WinCUPL and then program that, and then we'll start to assemble the board. Okay, so I've already compiled the PLD. I've shown that on numerous videos before, and now we're just going to program the programmable logic chip. So it's always a good idea to read the chip first, just to make sure you plugged it in properly. And then I'm going to load the JED file that we've just compiled. I'm just going to program that. Okay, so that's done. So we'll all be ready to plug everything in and connect it all up. Okay, so I've got some links here, some decoupling capacitors as well that I've added onto here. I've put on the labels and we've programmed our PLD. So I'm just going to lay out the board now. In fact, the address bus and the I/O bus and everything else is going to be over this area when we plug this in. So we want to have the address lines over on the side here. We need to allow for our 4 address lines to come in over here. So we'll just put that there. And then this one, we've got all the address lines are actually on this side. So it probably makes more sense to put this over on the other side here. And because this is a wider chip here, we need to decide whether we want the 2 holes on this side or on this side. So I think we'll have the 2 holes on that side and 3 holes on this side, because there's a lot more stuff going backwards and forwards here. So that looks like that should be sufficient for us. So just going to plug those in. What I'm going to do now is I will just speed this up and then I'll commentate over it. And we'll come back once everything's ready to connect to the main board. So just press the chips in and connect up the power lines. Then this is the lower address line, so A0 to A3, and the data bus coming in at the top there. Just put in the crystal, so it's very small from a watch. And then the chip select and the Motorola Intel, set to Intel. Another ground there. That's used to clear the CMOS RAM. Now we've got the pull-up resistor here, but in fact we need to move it over to the right so we can fit the battery in there. So I actually realised I needed to move that over there. Then putting in the RTC read, write and address enable, address strobe. Now we're just reconfiguring there so we can fit the battery in there. Just changing the connections to ground so we can fit that in there. Then that is the clear RTC, and then this is the address lines for A4 to A11, and then the output for the IRQ. Okay, so that's finished wiring up the board. We just need to remember to put the IO read, IO write and the IO A19 to A12 from the other decoder plug in there, but those lines are actually fairly close to here, so that should be fairly easy to put in. And then we're just going to carry some power over from the other board over onto one of these power rails, sets of power rails here. So now what we need to do is to put this onto the main board, hook it all up, and then we should be ready to update the software. Okay, so I've moved the board and I've got the camera over the bottom left corner of the board here. So this is where we're going to put in our little board here. So what I'm probably going to do is, when I get the second board in here, I'll work out how to fix this a little bit more securely. So we're going to be putting the data bus, it's going to be going over here. The address bus here will be going a little bit higher up the board there. And so what I'm going to do first of all though is just check that it's still working, and just going to boot this into PC-DOS 210 just to check that that's all working. We can see it's prompting us for the date here. At the moment it's the 1st of January 1980, and It's just a few seconds since the system booted. So you can see that it's working at the moment and that we don't have any date and time information. So just connecting up the power lines there temporarily, then feeding in the IO read and IO write. And this is the address line A12 to A19 signal, the reset and the interrupt lines, and now we're just wiring in the data lines here, and then these are the A0 to A3 lower address lines, then finally the higher address lines that go a bit further up the board. They're out of camera view. Okay, so that's all wired in now. It's a little bit rough and ready at the moment because when we add the IDE controller, then we're going to sort of reorganize this a little bit anyway. So we've got the reset line, we've got our IO read, IO write, and this is the IO A19, A12 line coming in from the other decoder. We've got our data lines and all the various address lines coming from here and here. So the next thing we need to do is to update the BIOS. So what we actually need to do is to change the configuration. So we need to add AT, RTC and non-volatile RAM. So this is really the CMOS RAM. So if we add those in, there were a few other minor changes needed to make to the BIOS. There was a couple of addresses that I needed to change. So the monitor needed to be moved up a little because there wasn't quite enough space. So once we've done those, we can then just go and run the make file. And that has completed without any errors, so that will have created a new binary file, and then we can just use this to write the just burn the EPROM. So I've already done that already, and so now we're going to turn it on and see whether or not we get any BIOS setup. Okay, so I'm just about ready to power this on. Now I did notice that I'd made a minor mistake in that one of the pins here, the one for the address strobe, was actually the wrong logic. So I'd assumed it was active low, and in fact it was active high. So when I first played around with this, it wasn't quite working, but I've corrected that. And just to show you where I'd gone wrong, so you can see here that the RTC write and RTC read are active low, but in fact the RTC address latch enable, address strobe, is actually positive. In fact, when I went through and checked out this gate here, these are OR gates, this is an OR gate. So in fact I had the signal here inverted. So when you get two zeros here, so IO write and the address select, then this should go to 1 and it should be 0 the rest of the time. So that was a small change I had to make. So I've updated the schematic. So previously this had a bar on the top. This one never had a bar, so I've now removed the bar from that. And then also I've now created version 2 of the IO decoder. I've changed the polarity of that signal there. We've also changed the polarity on the output, and in fact I've also put the combination of the 700 to 7F address ranges now on an external pin just for convenience. So I've programmed the PLD. I've also done a minor update to the BIOS just to make some of the text appear a bit clearer, and so now we're in a position to power this on for the first time. So I've installed the cell here, but I have reset the CMOS configuration in there. So the first time we power this on, we should get it as if it's blank and it doesn't have any configuration in it. And then what I'll do is to reboot, and then we'll have a look at configuring the setup. So just power it on. You can see we've got about 4.8 volts there, which should be more than sufficient. Now I'm just going to show the video screen as it powers up. And if we just boot the BIOS, so you can see it's a bit small. The NVRAM checksum's invalid, loading default values. Press F1 to run the BIOS setup. That is actually booting MS-DOS 210, PC-DOS 210 here, and it is asking for the date and the time. We'll just put those over. Now, in fact, the time is still showing as the correct time. The date isn't actually coming up properly there. So what I'm going to do now is to reboot this, and we'll do it in full screen mode so we can actually see this text a bit better. So if you press F1 to run the BIOS setup utility, Okay, so we can see now we've got the BIOS setup utility, enter H for help. So this gives us all the options, so we can change the floppy drives, whether we scan for BIOS extensions, enabling memory testing, setting the date and time, and print out current settings and then save the settings as well. So if we print out what the current settings are, so you can actually see there's a few defaults been there. So if we wanted to enable memory test, so we just go into M, yes, so that was already set. We want to set the floppy drive, so I'm going to set the first floppy drive to be 1.4 meg, and we'll also change help again. Second floppy drive I think should be disabled. So if we now print out the settings, now at the moment the date is not correct, and it doesn't look like the time is correct there either, so we're just going to set the date. The date is 2024-07-16. If we just do the time as well, so it's at 15:21. Okay, so if we just print that out now, so that looks a bit better. We've got 2024-07-15-21. If we now write that, that now should reboot. Now the PC DOS doesn't seem to be picking up the current date properly for some reason, so I need to look into that. But if we just put in date for the moment, you'll see in a minute there might be an explanation for that. But it is picking up the correct time, so it is picking up some of the RTC stuff, but otherwise it's not. So if you just type in time, and date, could be IR/W. EIR. So that's all appears to be working. Obviously this is all, floppy disk was last updated in October 1983. Okay, so I'll just reboot it one more time just to check to see if all those settings have been saved. So we're just rebooting it now. We can see there that we've got the 2024-07-16. Now it's still not picking up the correct date, but it is picking up the correct time. And if I just reboot one more time and go into the setup utility, so if you just print out, so sometimes you do get to see FF24, so I'm wondering whether there might be something there. So I've got the real-time clock working now. I will look into why the date isn't being picked up from PC DOS. It might be related to Y2K type issues possibly, but I'll look into that. And if we just have a look back at the main screen now, so we've completed our real-time clock and CMOS setup. In the next video I'm going to be looking at building an IDE disk controller and configuring an IDE BIOS so we can actually boot off a hard disk. And in the background I'm also looking at changing the floppy disk BIOS configuration to use programmed I/O rather than DMA, so hopefully I should be able to do an update on that in a couple of weeks' time. So if you don't want to miss out on future videos, please hit subscribe, and if you found the content interesting, please hit like. It just helps to make the videos available to a wider number of people. Thanks for watching.